Good day and welcome to part one of our discussion on substitution. To begin, let's start off with a bit of motivation. We have recently introduced the fundamental theorem of calculus, and we've seen that in order to evaluate a definite integral of a function little f, all we need to be able to do is find any antiderivative big F. That is a function where big F prime is equal to little f. And as long as we can find this antiderivative, we can evaluate that corresponding definite integral. So the observation we made previously and the observation I want to emphasize again, it is very important to be able to find antiderivatives. Finding antiderivatives allows us to quickly and efficiently evaluate definite integrals using the fundamental theorem of calculus. And from a very intuitive perspective, every rule of differentiation or every common differentiation formula should correspond to an antiderivative or an indefinite integral. So for example, if I asked you to differentiate the function sine of x squared, this would have previously been a quick and efficient problem. You'd say it's a composition, so we differentiate it with the chain rule. And we get back cosine of x squared, the derivative of the outside, evaluated at the inside, multiplied by the derivative of the inside. So if we were to write this as an indefinite integral, we would say that the indefinite integral of cosine of x squared times 2x is equal to sine of x squared, and the indefinite integral represents all possible antiderivatives, so plus c. In general, we can think about undoing the chain rule. The chain rule for differentiating the composition f of g of x states that we get the derivative of the outside, evaluated at the inside, multiplied by the derivative of the inside. So restating this as an indefinite integral, the indefinite integral of f prime g of x times g prime of x would simply be f of g of x plus c. And this idea of undoing the chain rule leads us into an integration technique which we will refer to as substitution. So let's now go ahead and state the substitution property and make a few observations along the way. The goal of the substitution property, in a sense, is to undo the chain rule. So if we want to integrate something that looks like f of g of x times g prime of x, note it looks an awful lot like what we see above, but it's not quite the same. But to try to follow this idea, what we are going to do is introduce a new variable u that is going to represent the function g of x. We think of this as being our substitution. So the first observation we want to make is we introduce a new variable u to represent the function g of x. So in terms of our integral that we start with on the left, g of x is going to simply become u. And what we would like to do is take this integral that starts off all in terms of x's and rewrite it so it only involves u's. So working our way through this, if u is equal to g of x, then we can differentiate u with respect to x. That would be g prime of x. And note, in our integral, we have this dx that we somehow need to put in terms of u's. And typically, when we see this quantity du dx, we think of it as being a single entity. But we don't have to. Individually, du and dx are quantities which are called differentials. And we could multiply both sides by dx and, separate it out. So du is g prime x dx. And note, very conveniently, that is precisely what we have remaining in our integrand above. So this integral starts off only involving the variable x, but we can rewrite it now so that it only involves the variable u. And this formula is what we think of as being substitution. And something I would really like to emphasize once again is that when we are using this method of integration, we go from all x to all u. So there's no middle ground. The independent variable that you have, x or u, is the only variable present. So all x to all u. And lastly, let me note the key idea before we jump into an example. And the idea behind using a substitution is a very simple, intuitive one. This integral that we're starting off with is difficult to evaluate. Think of it as maybe a complicated integral. What we would like to do is express it in this different form that's going to be simpler and easier to evaluate. So the key idea is to express a complicated integral in terms of a simpler integral. Once we have this simpler integral, we evaluate and then we resubstitute. So let's go ahead and illustrate this with a few concrete examples. When it comes to integration in Calculus 1, believe it or not, you are in a very good position. We have two methods for integrating. We can either somehow compare the integrand to our common table of antiderivatives, and that might require some algebraic manipulation. And if not, the only other method we are going to have is substitution. So for example, no matter how hard we try, we're not going to be able to algebraically manipulate this integrand to get any of the terms to compare to our common antidifferentiation formulas. So instead, our only hope is going to be using a substitution. And when we use a substitution, we need to select a choice for u. And the idea is going to be that we typically pick u to be something inside another function. And in this case, we only see really one thing inside another function. 1 plus x cubed is inside the square root function. So let's go ahead and try u equals 1 plus x cubed. And I say try because there's never any guarantee until we calculate out du and see if we can rewrite this integral involving all x's so that it only involves u's. So du would be the derivative of 1 plus x cubed, 3x squared, times dx. And note if we change the order we're multiplying by, just for convenience with this first example, we see that we have precisely what we want. The square root of u and 3x squared dx is precisely our du. So we can go from all x to all u. And once again, just to reiterate a point from earlier, we're starting off with a complicated looking integral, but once we've made this substitution, it's easier, simpler for us to evaluate. And that is the entire reason we made this substitution. So in terms of integrating, this is as good as it gets, a power of the variable. So when we anti-differentiate u to the 1/2 plus 1 is 3/2, 1 over 3/2 is 2/3, and we have an antiderivative of u to the 1/2. Something I want you to think about, is this our answer? A common mistake early on with substitution is to not resubstitute. The idea is we started off in terms of the variable x. Our answer needs to be in terms of the variable x. So each u needs to be rewritten in terms of the variable x. And we refer to this as a resubstitution. So if we resubstitute, note u is really equal to 1 plus x cubed. So this would be 2/3 the quantity 1 plus x cubed raised to the 3/2 plus c. And once again, this is called a resubstitution. A couple reminders. When we are integrating, remember, this is essentially what your work should look like. You align things vertically in a column using equal signs, integral symbols, dx's, du's, what we call differentials, at each step. If you run out of space, simply draw an arrow up over to the right and start a new column. When you're doing a substitution and you have these quantities, say u and du, don't interrupt your work by writing those in between equal signs. Instead, that is side work that should be done to the side of the page. Let's now investigate a slightly different example. What if we don't have that 3 and it's simply x squared times the square root of 1 plus x cubed? Well, the idea is exactly the same. There's no way we can manipulate this integrand algebraically to apply our common anti-differentiation formulas, so the only remaining possibility would be a substitution. And when we do a substitution, we try to choose u to be something inside another function. And not only do we try to pick something inside another function, we want to pick the largest possible inside function. And with that in mind, we'll choose u to be 1 plus x cubed, just as we did above. So du would be the derivative of 1 plus x cubed, 3x squared, times dx. And now comparing to our integrand, and for convenience, once again, maybe I'll rewrite the order. So the square root of 1 plus x cubed times x squared, dx. 1 plus x cubed is our u, and somehow if this is going to be successful, the x squared dx has to be written in terms of du. And we can do that very easily by just dividing by 3. Note this is equivalent to saying 1/3 du is x squared dx. So we can go from all x to a simpler integral only involving u. We have the square root of u times 1/3 du. 1/3 is a constant, so I'll go ahead and pull that out front. We now anti-differentiate this simpler function, which we've already done above. It's 2/3 u to the 3/2 plus c. And whenever we use this method of substitution to evaluate an indefinite integral, our final step is always going to be to resubstitute. So each u needs to be replaced once again with a 1 plus x cubed. So this would be 2/9 1 plus x cubed to the 3/2 plus c. And once again, let me just reiterate. As a student of Calculus 1, you are in a very good position when it comes to integration. We have essentially two methods. We can either directly or through algebraic manipulations work back to our formula of common antiderivatives or indefinite integrals. Or our second method is a substitution. And when it comes to a substitution, the key thing we need to get started is a choice to play the role of u. So there should be, in a sense, kind of guidelines or good choices for u. So I would just note that good choices for u include the following. So the first and foremost is you want to pick u to be something inside another function. And when you are choosing your u, remember there is never any guarantee that something will work just because it's inside another function, but that's an indicator of a choice for u that we might try. And the second observation I want to make related to a good choice of u is you want to look for a function derivative pair. And what I mean by that is you have 1 plus x cubed, a function, and outside of that square root, you get its derivative. So a function derivative pair. Up to a constant, x squared is the derivative of 1 plus x cubed. So look for a function derivative pair. And this completes our introduction into the method of substitution, which we'll continue exploring in our next video. So stay tuned. Take care.